Oh, alright. Welcome back. Previously we talked about example 1-1 on viscosity and shear stress. Okay, now we will go to a different topic. Okay, that is related to a property called the pressure. Okay, pressure, as you know, is simply force over area. Okay, what kind of force? If I have an area, okay, the force acting perpendicular to the surface is the pressure force, and the unit is pascals, okay, or Newton per meter square. And on the notes there is a brief description of what it is and what is the typical value of okay, maybe it's not here, but the typical value of atmospheric pressure is about 1.01 kilopascal, okay, which is actually 101 kilopascal, okay, which is about 101,000 pascals. Okay. There is another unit which is used to describe such big values, and that is the bar. 1 bar. 1 bar is typically 100 kilopascals, or 10 to the power of 5 pascals. Okay. This is usually used in many industrial applications, okay, and it's written over here. 1 bar is 10 to the power of 5 pascals. So having talked about the unit, let's talk about pressure in the fluid, okay, which is the hydrostatic pressure description over here. Okay, let me try to just briefly talk about this. So imagine this is the free water surface, right? And there is a certain area that is submerged under this surface. And let's say this area has an area of A, and it is at a depth of h. Okay, so the force that is actually acting on the area A right now is literally the weight of the liquid above, okay, which means this column of liquid. So what is the weight? The force on A is the weight of the liquid column. So the liquid column has a certain volume multiplied by the density of the liquid, right? So the volume is basically cross-sectional area A multiplied by H. H times A times rho. This is the force. Okay, and you also know that pressure is force divided by area. So in fact, the pressure is H. Okay, wait. Okay, I short of a G over here. Okay, because mass times gravity. So there's a G over here. So it's H A rho G over A. Okay, so in fact pressure can be simplified into rho G H. This is the depth, this is gravitational acceleration, which is 9.81, and this is the density of the fluid. Okay, so this is your hydrostatic pressure. Now, if instead of looking at submerging underwater, right, what if we put this under the atmosphere? So imagine this is the ground, and you are here. Okay, actually what is above you is this column of air. Okay, this column of air over here. So in fact, right, the so-called atmospheric pressure is also a form of rho GH, where the density is the density of air. Okay, so if you go by this logic, anyone who is up in the mountains has a shorter column of air. So the atmospheric pressure at the mountain is actually lower than the atmospheric pressure at sea level. Okay, and likewise, if you have someone at a very deep canyon over here, he will experience a higher atmospheric pressure because simply the column of air is taller. Okay, so this is a brief description. And next, we are going to talk about the buoyancy forces. Okay, having gained the basic understanding about pressure, we can talk about the buoyancy force and Archimedes principle, which is on page 11 of the notes over here. Okay, but I'm going to try to summarize it for you right now. Suppose I have a floating object, okay, floating in the water. So this is H2O, right? And this object, part of the surface, part of the volume is above water level. So let's call this VA, okay? And part of the volume is submerged. So let's call this VB, okay? So the idea is this: if this object is floating on water, it will have two forces acting on this particular object. One is the weight of the object, okay, which is mg. The other is actually the buoyancy force. Okay, if we take the equilibrium of forces, okay, you have your weight and you have your buoyancy force. You can write W equals to FB. Okay, so the weight is mass of the object times G. Buoyancy force is the weight of the water that is supposed to be here. Okay, the weight of the water that is supposed to be occupied by this volume here. Okay, so it is the mass of water displaced multiplied by G, right? Mg equals mg. So what matters is how will you get these masses. Mass of object is volume times density. So volume of object times density of object times G. This one is also volume of displaced water times density of water times G. Okay, volume of object is basically the whole thing, VA plus VB. And density of the object is just the density lah. Okay, and actually since both sides have gravity, right, we can cancel out. Okay, and leaves us with this. The volume of displaced fluid is the part that is submerged below the water, so it is VB. Okay, and volume of then density of water. So if you move this around, you will realize that the density of object over density of water is equals to BB over BA plus VB. Okay, what this means is that if your object is floating, it should have a density that is less than the density of water, right? So if you compare the density between the object and the water, this number, right, you see VB over VA plus VB has to be less than 1. Less than 1. Okay? And this will give, then with this you'll be able to find the density of the object. Okay? Now if the whole object is submerged, okay, it's still floating but it's submerged. What does that mean? It actually means that the submerged volume is equals to the object volume. So your density of object, right, over density of water is actually 1, right? So it means that the density of the object is the same as the density of water. And just so happens that, you see, it reminds us of a property that we have discussed about very initially, relative density. RD, or specific gravity SG. Okay, both are the same. So this one will actually give you the ratio of the volume will actually give you the relative density of the object. Okay, so that's the thing that you can take away with you. My advice will be always to start with this equation. Okay, sum of forces. The weight must be balanced with the buoyancy force. But I will tell you that not every time this case will happen. Why? Because there are some times when the question, apart from the weight and the buoyancy, it will also have a cable that is attached to the object, right? And this cable is supposed to have a tension force pulling the object up. So this tension force, if you remember your mechanics, this is T. This is a tensional force. Okay, so if you look at this picture, right, the balance of forces will no longer be just weight equals to buoyancy force, because your weight is now accounting for the buoyancy force and also the tension. Okay, then you should start from this equation to approach your problem. Okay, so you put your volume, your density, and your weight. You put the displaced volume and the displaced density of the liquid here, and given tension, and etc., etc. You can find the unknowns accordingly. All right.